Hello everybody and welcome back to another video on my series for calculus. Last time we discussed functions, what they are, how we define them, their domains, their ranges, and some special properties that they might hold. And today we're going to expand on that idea and see how we can use functions to model real world problems. Now, you may have realized that the audio got an upgrade. I got a mic. I got a mic because my last mic would keep clipping, and every single time I would have to go in through the editing software and constantly just look for like clips and reduce the audio so that it wouldn't like blow your guys' ears out. But it wasn't perfect, and I realized I needed an upgrade. So I got this mic off eBay. Not eBay. I got this mic off Reverb. It's used. Hopefully I did not get ripped off. If I did, I might just cry. And I don't want you guys to see that. So let's hope it works. Alright, to start off, I kind of want to describe what a mathematical model is. So a mathematical model takes some real world phenomena that we see and it tries to describe that process mathematically. So one of the first steps in doing this is identifying what are the dependent and independent variables in some process. If we take a ball that is falling in the air, the independent variable is the amount of time that the ball falls for, and the dependent variable is the position of that ball. The position of the ball depends on how long it has been falling for. Now, the thing is that reality is very complicated, extremely complicated, and as much as we want to try and create this perfect mathematical model that is able to predict everything, it's almost impossible. There's so many factors that come into play. So a lot of the times when we make these models, we're making assumptions to kind of make the math easier. Because if we don't make those assumptions, then it's incredibly difficult, if not impossible, to create a model for these processes. But it's also important that even though we make these simplifications, that our model is still accurate, because we can make small tweaks and we can ignore certain factors while still having something that gives us accurate results. But going back to the intro video where I discussed throwing a ball and it goes in a straight line, that's very easy to calculate. It's a very simple model, but it doesn't give us accurate results about what happens in the real world. So it's kind of a balancing act between making this model simple enough so that we can describe it, while also having it give us good, accurate results that we care about. So a lot of the times when we talk about things that happen in the real world, there are physical laws which govern those interactions, and we can use those physical laws to help us make our model. Sometimes, though, there aren't going to be any laws. There isn't going to be some formula for us to follow. And in those cases, what we're going to have to do is we're going to have to gather data and look for a trend. Plot those data points and see if there's some pattern which we can discern. And then finally, once we do have our model, we can analyze it mathematically. We can use it to make predictions. We can use it to form some sort of conclusion about the process. And then we can test that conclusion with any future data points. And if our model holds up to our tests, then that's great. Our model works. But as soon as our model breaks, as soon as we see a data point that deviates from what the model might predict, then we have to tweak it a bit. So let's talk about how we can use those functions we discussed in the last episode to create those models. Well, the most simple model that you're going to see is typically going to be a linear model. So you should know, hopefully, that the graph of a linear function is described by a slope, which we call m, and a y-intercept, which we call b. If we can find these two parameters, m, the slope, and the y-intercept, b, then we can draw our function of a line. Every function that we are going to discuss in this episode is going to have some special property about it. And the property that linear functions have is the fact that they change at a constant rate. So here what I've done is I've created this little table. If you look at this table, you notice that each time we increase our x value by 0.1, we increase our function value by 0.3. 1.1 to 1.2, our function goes from 1.3 to 1.6. When we go from 1.2 to 1.3, our function value goes from 1.6 to 1.9. So you see that there's this ratio. Our function value is changing 3 times faster than our independent variable is. And the ratio is constant throughout this whole entire table. You can see that it's a straight line. It's linear. Our function value is changing at a constant rate with respect to our independent variable. So, because our function value is changing 3 times faster than our independent variable is, we say that the slope of this function is equal to 3. So the slope is just a factor by which y is changing with respect to x. Knowing that this slope of this function is equal to 3 and that our starting point here at x is equal to 1 has a function value of y is equal to 1, let's try and predict what value this function is going to have at x is equal to 2, x is equal to 3, and x is equal to 4. Go ahead and take a moment to think about what the function value is going to be at those points. So we've already established that the y is changing 3 times faster than the x is. So if we look at what the value of the function is at x is equal to 2, when x goes from 1 to 2, it changes by 1, which means that the function must change by 3 times that. So the function changes by 3. So then we know the value of the function at this point, x is equal to 2, is going to be 3 plus 1, which is equal to 4. Applying that same idea. The x changes by 1 when it goes from 2 to 3. And we know that the slope is equal to 3, so the function needs to change by 3, and it goes to 7. And again, x changes by 1, so the function changes by 3, going to 10. As long as we know how much it changes by, we can also find how much the function changes by, because that ratio is always going to be constant. That ratio is always going to be equal to 3. That is what makes our model linear. So let's now look at an example in the book that I am using. Excuse my dog in the background. Part A says, as dry air moves upwards, it expands and cools. If the ground temperature is 20 degrees Celsius and the temperature at a height of 1 kilometer is 10 degrees Celsius, express the temperature T in Celsius as a function of the height h in kilometers, assuming that a linear model is appropriate. Now, for this problem, we are making an assumption. Our assumption is that our model is going to be linear. And because of this assumption, we already know what the form of our equation is going to be. We know what the form of a linear function is. So whatever our equation is, it's going to have this form. And we have 2 unknowns in this case. We don't know what the slope is, and we don't know what the y-intercept is. So those are the 2 parameters which we need to find. So reading this problem, ask yourself, what is the independent variable and what is the dependent variable that we want to account for? Well, it's given to us in this problem. It says that we want to express the temperature, which is our dependent variable, as a function of the height h, which is our independent variable. So we can rewrite this function as the temperature as a function of h is equal to our slope times h plus our y-intercept b. At this point, we ask ourselves, what are we given? What data points do we have? At ground level, which is h is equal to 0, the temperature is equal to 20 degrees Celsius. At a height of 1 kilometer, it is equal to 10 degrees Celsius. we have 2 points. We have 0, 20, and 1, 10. These are the 2 points that we know must be in our model. So we can use these points to find out what these parameters are equal to. So looking at these pair of points, which would you say is the most useful one? Which do you think we should use first in order to find either the slope or the y-intercept? Which would be the best one to use? If we plug in h is equal to 1 in this case, what do we get? Well, t at h is equal to 1 is equal to m times 1, which is this m, plus b. And this is equal to 10. But this doesn't really tell us anything. This just tells us that the slope plus the y-intercept is equal to 10. But we have no way of solving for either of these. So clearly, we're not at that point yet where we can use this data point. If we use our other data point, 0, 20, notice how our m term here, our slope term, is going to be equal to 0. And that eliminates our unknown parameter. It eliminates it, and it gives us a known value, which was going to be equal to b, which we don't know yet. So t at h is equal to 0 is equal to m times 0 plus b, which is equal to 20. That's our known value. And this just tells us that b is equal to 20. There you go. We have our first parameter. We can use it along with the known data point that we were given initially to find what the slope is. T of 1 is equal to m times 1 plus b, which is 20, and that is going to be equal to 10. So then m is equal to negative 10, and we found our slope, right? Our final equation. T of h is equal to negative 10 times h plus 20. We want to plot this graph, and we already have 2 of our plot points. Going back to this idea that the slope is a description of how fast our function changes with respect to x, we can find any other point that lies on this line. So here, what is our function value going to be at h is equal to 2? Well, we know that the ratio in which our function value changes with respect to h is equal to negative 10. So if h changes by 1, then t changes by negative 10. And our value at h is equal to 2 is equal to 0. And we keep applying the same idea. So at h is equal to 3, our function, oh, actually, I made a mistake here. This is equal to 3, 0. No, I made another mistake. Excuse me, I'm very tired. This is equal to 2, 0. And then this point is equal to 3, negative 10. And then at 4, we have 4, negative 20. And you see that our, well, it's it's not a perfect line. It's not a perfect line, but that's not because the math is wrong. That's because I'm terrible at drawing graphs that are to scale. Really, it would be better if I did this on Desmos, but whatever. For the sake of the example, I wanted to do it by hand so that you guys can see what a slope really is. So we know what the value of the slope is, but what does it represent physically? Like at this point, we just know that it's a number, but we want to contextualize it to the problem. So in this context, the slope is representing how much the temperature drops each time we go 1 kilometer higher in altitude. That's a physical description of what the slope represents. Each time we go up an extra kilometer, our temperature drops by -10 Celsius. Let's try and make some predictions. Let's ask ourselves, what is the temperature going to be at 2.5 kilometers? H is equal to 2.5, and that is plus 20. And if you plug this into a calculator, you will find this is equal to -25 plus 20. So then we get that our temperature at 2.5 kilometers is equal to -5 degrees Celsius. Now this was a pretty easy problem because it gave us the model that we had to use. It told us that we had to use a linear model. But just as I described before, we aren't always going to have some assumption that tells us what model to use. So let's look at an example where we just have a table of data points that we need to see if there's a trend for. So here we have a table that I pulled from the textbook, and it lists the average levels of carbon dioxide in the atmosphere that was measured in parts per million at the Mayan Loa Observatory. I'm probably butchering that, but whatever. Doesn't matter where it was measured. And what we want to do is we want to find a model for these data points to see if we can make some sort of predictions. So we're not told what model we need to use for this problem. We can't make any assumptions. Only thing we can really do right now is plot these points and look for some sort of pattern. So I went ahead and plotted these points on Desmos. You can look at this and say, okay, a linear model is most likely going to be an accurate representation of this process. We've established which model to use. Now is a question of how do we find the equation for it? There is an infinite amount of lines that we can draw to try and best represent the trend of these data points. It's probably best if we draw some line that is as close as possible to these points. The closer that our line is to the observed data points, the better. That tells us that it is a good fit. So for the sake of solving this problem, I'm going to say, okay, I want to draw a line that goes between our first point here and our second point here. In order to draw that line, we need an equation. So we've established that we want to use two data points. Our last data point here, and our initial data point. So because the slope is just a description of how fast the CO2 levels change with respect to the year, the question we should ask ourselves in this case is, how much do the values change by? How much does our function change between our 2 points of interest? So our 2 points of interest is the function value at TF, which is our final point, and the function value at TI, which is our initial point. Taking the difference of these two values tells us how much does our initial function value change by in order to reach our final function value. So this is equal to 404.2 minus 338.7. If you plug that into a calculator, you will find that the difference is equal to 65.5. So then, between our 2 points, the function increases by 65.5. So now we know how much the CO2 levels change by. We also want to know how much time elapses as that change occurs. So delta T is equal to TF minus TI, which is just equal to 2016 minus 1980. And that is equal to 36. So we have our two differences, but the slope is the ratio of these two. So the slope is going to be equal to the difference in the CO2 levels divided by the difference in the amount of time that elapsed. And that is approximately equal to 1.819. So now we have our slope and we have our point that the slope is going through. So we have enough information to write the equation for our line, but we have to use a special form of that equation. And hopefully you guys are familiar with this form. This is the point slope form for the equation of a line. x1 and y1 here is the point which our line is going through, and m is our slope. We know all of these values, so we can just plug them in. We know that y1, in this case, we're going to use the initial point. y1 is equal to 338.7, which is equal to the slope, which is 1.819 times x minus x1, which is 1980. X minus 1980. We add 338.7 to both sides. So this stays the same. Oh, I made another mistake. I am not in my element today, guys. I don't know what is wrong with me. So we add 338.7. And we can distribute this constant number to the term inside the parentheses. So distributing that, we find 1.819 times x minus 1980 times 1.819, which is about 3,601.62 plus 338.7. And you can just do this on a calculator. This gives us the function of our equation, which is 1.819x minus 3262.92. And I just realized that I've been using the wrong variables this whole time. This x should be equal to t because we're not using x, we're using t in our original definition here. So I'm being inconsistent with my variables, but you get the idea. So now we have some line that we think is going to be a good fit for our data. Let's plot it and see if it's actually a good fit. So here we have the function that we just solved for. I just plugged it into Desmos. And looking at this graph, yeah, it's okay. It's definitely not perfect. We do have our line going through these 2 points, our initial point and our final point, which is what we wanted. However, the problem is that all of our observed data points, other than those two, are less than what our model predicts they should be. It gives us a decent fit, but it's not perfect. And it could definitely be better. Just imagine if we moved this line downwards just a little bit. It's not going to go through our points. However, it's going to be closer to all the points in general. And that's our goal. We want this line to be as close as possible to all of the points, not just two of the points. This process that we just did where we pick 2 points and we define a line that goes through them, it's okay, but it's definitely not the best approach that we can take. There is a much better way that we can do this, and it is called linear regression. Linear regression is something that is studied in statistics. Unfortunately, we're not going to be going over linear regression in this course. However, there are calculators online which we can input our table of values. We can input these values and it will calculate what the slope and the y-intercept of our line of best fit is. So let's go to one of those calculators, plug in these values, and see if we can get a better line. So here what we have is a linear regression calculator. And pretty much all you have to do is you have to plug in your inputs and your outputs, and then after you create your table, you just calculate it and you get your results. So right off the bat, looking at this graph, it looks like it's a lot better than the one we had before, but I'll plot this on Desmos just to compare and contrast the two. And it tells us that the calculated slope for this line is 1.782 and the y-intercept is -3.193. So I'm going to head and plot this on Desmos and compare it to our previous approximation. This is the equation that we got from the calculator, and if we just get rid of this, this is what our new line looks like, our new line of best fit. Comparing this to our old line, which looks like this, it looks a lot better. It does. It looks way better. Unlike our previous estimation, this line doesn't necessarily go through any points. It gets really close. Like it almost goes through this one, it almost goes through that one, but it doesn't go through any of the points directly. And yet, it's a better approximation. The reason why is when we do a linear regression, we don't just focus on 2 points. What we do is we find a line that minimizes the distance between this line and every single one of these points. This line is constructed so that the distance between it and each individual point is as little as possible. That is the best way that we can create a line of best fit, and we can see that it is much better compared to the one that we had before.